A black hole, an object so dense that its escape velocity exceeds the speed of light, functionally creating an inescapable region. Or at least that's what most of us understand it to be. It turns out that black holes are not escapable, and for that matter, not even black. In 1975, Stephen Hawking applied quantum field theory to a curved space-time metric around the event horizon. Vacuum fluctuations resulting from the uncertainty principle spontaneously create virtual particle-antiparticle pairs. Normally these two come back together and quickly annihilate. However, if this happens very close to the event horizon, the particle with negative energy will be more likely to fall into the black hole than the one with positive energy, permanently separating the two and transforming them into real particles. This causes the net effect of positive energy escaping and negative energy entering the black hole, ultimately reducing its mass. The effect may seem negligible, but Hawking showed it to be significant on universe lifetime timescales. Escaping energy implies that black holes radiate at a small but unignorable rate, known as the Hawking temperature. A somewhat unexpected but convincing result is that this radiation turns out to be blackbody emission. Although initially met with intense skepticism, Hawking radiation has been re-derived through a variety of methods over the past several decades and is now widely accepted. However, it has some concerning implications. In the emission process, only mass and energy are preserved. This means that anything which enters a black hole will eventually come out, but all information associated with it will be lost, violating unitarity. To understand Hawking radiation in a way in which information can be preserved, Hawking proposed that the radiated particles become entangled with the area around a black hole, so that, in principle, information can still be extracted from the radiation. But this creates an apparent information paradox. For instance, imagine our old friends Alice and Bob are hanging out near a black hole, when suddenly poor Bob falls in. By comparing with Bob, Alice should be able to get his information. However, Alice would also be seeing that same information within the radiation, which violates the no-cloning theorem. This paradox remains unsolved and implies that either several key understandings of black holes need to be revised, or that quantum unitarity itself should be re-examined. It may be possible to actually observe Hawking radiation in nature. The smaller a black hole is, the shorter a virtual particle will need to travel before becoming real. This means that the emission rate, and therefore the temperature of a black hole, will increase the smaller it becomes, leading to an ever-increasing rate of evaporation. The black hole will eventually disappear completely in a final, brilliant burst of gamma radiation. For a typical black hole, this process would take much longer than the lifetime of our universe. However, small primordial black holes would have much shorter lives comparable to the current age of the universe. If so, they would currently be emitting potentially observable X-rays and gamma radiation, and we may also be able to see flashes of energy around us as they evaporate completely. However, these emissions would be relatively faint. The best existing candidate to detect such signals is the Fermi Space Telescope. It is currently searching for these faint gamma sources, but has yet to make any detections. We can also look for evidence of this phenomenon by studying lab analogs to black holes, and CERN's Large Hadron Collider has the potential to create tiny black holes. Such black holes would terminate almost instantly, producing a burst of energy and proving the strongest evidence yet. Although it may be a while before any such confirmations are made, Hawking radiation has already had a profound effect on the physics world. Implications such as the information paradox force scientists to reevaluate several major black hole and quantum principles. Most notably, this is the first discovered process which is only understood through the application of both quantum and classical frameworks, and could be the initial link needed to achieve the elusive theory of everything.